let's consider an example in which we mix two solutions together. We're going to mix together potassium chloride and silver nitrate. These are both aqueous solutions. Now I'm telling you that on here, but you can also think about solubility rules. Potassium and nitrate, always soluble. What I did is I predicted the products. What happens when you mix these two solutions together is you form a white precipitate on the bottom of what looks like a colorless solution. And so I predicted these products, and using solubility rules, I determined what was the aqueous solution that was colorless and what was the white solid on the bottom. And I found, using solubility rules, that silver chloride was that white precipitate that was on the bottom. Now, these are macroscopic observations. This is what we can see. What I want to focus on with this video is looking at the microscopic level and looking at particle diagrams. And these particle diagrams that I want to look at are going to show us why net ionic equations are useful and how to represent chemical equations at the particle level. So what we're going to start with is we're going to start with particle diagrams of the reactants, just to start off the overall diagrams of the reaction. So what we're going to do is we're going to start with our reactants. Okay? If we are mixing two solutions together, that means initially we have KCl in one container, AgNO3 in the other. So what I did is I simply represented them as particles. Now it's hard to see, but the red circles are K+ ions, and the green circles are Cl- ions. Now if you notice, they're separated. Well, why are my potassium and chloride ions separated? Well, it's a soluble ionic compound, which means it's a strong electrolyte. It dissociates into its ions. So that's how we have to represent it at the particle level. Now if we look at silver nitrate, same thing. These black circles are the silver ions, and then we have the nitrate ions. They also are separated. We have the silver ions floating around, we have the nitrate ions floating around. If we were to stick a conductivity meter in each of these solutions, it would actually light a light bulb, because both of these solutions are going to conduct electricity because they are strong electrolytes. Now, just something to make note of, both of these solutions are colorless. So before we even start the reaction, we have two colorless liquids in two separate containers. Now, if you notice, with each of these diagrams, I drew 3 K+ ions, 3 Cl- ions. So what that means is I would have 3 moles, 3 molecules of KCl. Now if you look at the silver nitrate container, you also have 3 silver ions and 3 nitrate ions. Now why do you think it's important that I drew the same number? Well, if you look up here, KCl and AgNO3 are in a 1-to-1 ratio. That means however many KCl molecules you have, you need the same number of silver nitrate. Okay? You have to keep the ratio the same. We're going to assume that this reaction goes to completion, which means you need equal number of molecules or formula units of KCl as silver nitrate. And so this represents the particle diagrams of our reactants. What we're going to look at now is what we see after the reaction is complete. So after the reaction is complete, we have both of our products in the same container. Right? You poured the two solutions together into the same container. So we have KNO3, which we already determined was aqueous using solubility rules, and we have this white precipitate of silver chloride. Now, if you look at this particle diagram, you see on the bottom we have the Ag+ ions and the Cl- ions come together. Okay? They came together because this is our solid. You have to represent a solid in a particle diagram. But then notice that you still have these ions floating around in solution. Well, why do you have the K+ and the NO3- ions separated again? Well, they're soluble. They're a soluble salt, they're a strong electrolyte, they're what are floating around in solution. Now if you take a look, I still have 3 K+, 3 NO3, and I have 3 AgCl molecules, if you think about it. Okay? I did not gain or lose any mass. The law of conservation of mass still takes effect even when we're talking about particle diagrams. So my number of total ions didn't change. What changed is the way that they were arranged. We still have our K plus and our NO3 minus ions floating around. That's why those are our spectator ions. They were ions before, they were ions after, and now we have these AgCl, the solid, at the bottom of our container. That's our precipitate. So if we were to write the net ionic equation for this reaction, we would simply be showing the formation of this solid at the bottom of our diagram. The net ionic equation is just showing the solid, in this case, that was formed, and we ignore all of these ions that are in solution.